This is a radiofrequency-driven, inductively coupled xenon plasma toroid apparatus. I built it. Not only does it look captivatingly beautiful, explaining the plasma effect requires digging into some really fascinating fundamental physics. In this video, I'm going to do my best to give an overview of what's going on here, both in terms of the actual physical effect as well as the driver electronics. I'm far from the first person to build a device like this. My work is directly based on previous builds by BackMaxI, Steve Ward, Human, and others. The general approach to creating the plasma toroid effect seems to be using a large, hand-formed copper coil with the driver electronics stacked underneath, but I had the clever idea of combining the coil into a single unified circuit board. Also, unlike other devices, which generally require manually grinding the glass globe against the coil to start the arc, I've got push-button start. My device also runs off of USB-C. I'm going to talk more about the electronics involved here, as well as this beautiful circuit board sponsored by PCBWay. But first, what even is this shimmery, glowy plasma donut? Let's start with a basic phenomenon of physics. Electrical current creates magnetic fields. A wire carrying current will produce a surrounding magnetic field which wraps around the wire's circumference. On the circuit board, this big arc surrounding the glass globe is a conductive loop, which makes one lap on the top side, then another identical loop underneath. This is the main drive coil, and it's carrying an alternating current at about 800 peak volts, a few amps, and a frequency of about 13 megahertz. The magnetic fields which wrap around this conductive path add up to create one combined field in the coil's center. Because the coil is carrying AC current, the orientation of that field is constantly flipping back and forth 13 million times per second. If we imagine putting a ring of solid copper at the center of the coil, the changing magnetic field would push the conductive material's mobile electrons back and forth around the circumference. That movement is an AC electrical current in the ring. The inside of this glass globe is filled with xenon gas, element 54 on the periodic table. The xenon inside is at a very low pressure, just about 2% of Earth's atmosphere. In regular, non-ionized neutral gas, electrons are tightly bound to their atomic nucleus. Neutral gas can't really conduct electrical current. However, ionized gas, plasma, is extremely conductive. In a plasma, electrons have been ripped away from the nucleus and are free to go zooming around. In the toroid's steady-state behavior, its loop of plasma is electrically conductive and behaving almost exactly like the copper ring we imagined earlier. Wherever the xenon is already ionized, that's where there's mobilized electrons which can be accelerated by the coil's changing magnetic field. Those zippy little electrons are able to bonk into adjacent atoms of xenon and knock their electrons loose in turn. The net effect is that the shape of the visibly glowing ionized toroid is more or less self-sustaining. It's able to move and undulate, but there's continuity to the way it moves. I'll go over how the toroid is actually started a bit later in the video. Since the plasma toroid itself is super hot, the toroid tries to drift upwards due to convection in the xenon gas. At low power levels, the toroid can float perfectly stable in the center of the globe. Higher power levels result in a more unstable dynamic motion. So, why is the ionized area a defined donut and not a more diffuse disk? What I think is going on here is the result of another electromagnetic effect called pinch. Once the charged particles in a plasma start moving, that motion then generates its own magnetic field. This field causes a pulling together force in areas where electrical currents are moving in parallel, and a pushing apart force where the currents are anti-parallel. So each side of the toroid where the currents are moving in parallel bunches up, and the center repels itself open. This phenomenon is part of why xenon is used for the plasma toroid effect. For reasons that I don't yet understand, arcs in low-pressure xenon have a greater tendency to form narrow filaments. Other folks have tried replicating the toroid using other gases, and are much more likely to observe diffuse glows of plasma rather than the sharp and nicely defined toroids. But how am I actually creating high-voltage radio frequency power and pushing it through the drive coil? This kind of RF analog electronic device might seem arcane, but I can actually outline the core principles in just a couple of minutes. The primary drive coil is acting as an electrical inductor. The way the current path loops back on itself makes the coil interact with its own magnetic field. As a result, that magnetic field is able to store energy. On the end of the drive coil, we've attached a capacitor. This is a basic electronic component that stores energy in the electric field between two very closely spaced metal plates. For my plasma apparatus, I'm using these tiny chip capacitors. Both of these components can store energy, but with AC currents, the way they each accumulate and release that energy is 90 degrees out of phase with each other. If an inductor and capacitor are connected together in series, they end up sloshing that energy back and forth between themselves. This behavior is almost perfectly analogous to a physical mass bouncing up and down on the end of a spring. This arrangement of inductor and capacitor forms what's called a tank circuit. Every tank circuit has a natural resonant frequency. For my inductor-capacitor combo, it's about 13 MHz. If you feed a tank circuit with an AC source tuned to its resonant frequency, it'll respond just like any other harmonic oscillator. The amount of energy present in the system will progressively ramp up. This is, mathematically, the same system behavior as repeatedly pushing someone on a swing, a singer breaking a wine glass, etc. The resonant tank is the beating heart of this entire apparatus. Its oscillations are what's creating the intense magnetic fields driving the toroid. To actually drive the tank circuit, we have a MOSFET, a kind of voltage-controlled switch that's a close cousin of the transistor, which is being rapidly turned on and off by some control signal. Each time it switches, current flowing through this feed inductor is alternately forced either into the tank circuit or allowed to pass to ground. Each pulse, timed just right, adds a bit more energy into the tank. We want to switch the MOSFET on and off at the same resonant frequency as the tank circuit, but rather than trying to perfectly tune its timing manually, let's instead generate a control signal using a feedback network. A second capacitor forms a capacitive voltage divider, so now the MOSFET is being driven by an AC signal whose amplitude is some fraction of the voltage present in the tank. That covers the AC component of the drive signal, but the DC component, the baseline voltage, still needs to be provided. To do that, we'll use a few resistors to divide down some fraction of our power supply voltage. For practicality, a potentiometer, a variable resistor, lets us use a physical knob for control. And now, all that's left is some implementation details. A voltage-regulating Zener diode stabilizes the DC reference. An additional capacitor stops radio frequency energy from leaking all over the rest of the circuit. A transient voltage suppression diode protects the MOSFET from getting fried from any overvoltage on the control pin. And one more low-value resistor adds a bit of helpful phase delay to the MOSFET's control signal. Finally, in the real circuit, some of the components are doubled up so that heat is a bit more distributed. The entire apparatus uses between 30 and 60 watts. For most of the shoot, I've been powering it off of this USB battery bank. I know I said I built this, but that's admittedly a slight oversimplification. The modern phrase would be something like, designed and assembled in the United States by Skyguided using globally sourced components. The globe itself, the xenon globe, was handmade in Massachusetts by plasma artist Wayne Stratman. You should check out his work. And the circuit board was manufactured by PCBWay. A traditional circuit board uses a fiberglass base, which is a sort of semi-translucent drab olive green color. Then there's the actual copper traces, which are chemically etched, And finally, the top surface is an opaque layer called the solder mask, which is designed to protect the board. This is traditionally green, but these days is available in all kinds of other colors. However, in my board, the underlying fiberglass has itself been dyed this deep black. Then there's the same copper, and the top layer, the solder mask, is totally transparent. This gives this board this really striking high contrast appearance, where you see the copper traces fully exposed in their natural color. It's a bit of a specialty product. You can't order this kind of board just anywhere, but dang, it's cool. A key goal of this build was to run the plasma toroid without needing any external support systems. Most folks who build this, and myself in earlier prototypes, have to leave the apparatus hooked up to an oscilloscope in order to determine whether or not the circuit has started oscillating. It's also standard practice to monitor the current draw. Not wanting either an attached scope or a panel current meter with numbers to clutter up my board, I had to find a different way. Check this out. Here's an LED and a resistor. Here's a random bit of wire. Wrap the wire into a little coil. And it lights up when the circuit is oscillating wirelessly. This is the same fundamental phenomenon as what's inducing electrical current within the toroid. The loops of wire are coupling to the changing magnetic field. You may have wondered what's up with this whole part of the circuit diagram, or noticed this little spirally guy on the circuit board. The spiral on my circuit board is the same as the freestanding loop of wire and LED, only integrated. The non-contact pickup might honestly be the part of this build that I feel most pleased with. It's an elegant solution and it requires 0 additional components. Earlier, I talked about how the toroid effect works in the steady state case, but that doesn't explain how to actually start the toroid. If I just crank the knob, even at maximum, the magnetic and electric fields from the primary drive coil aren't strong enough to rip the first few electrons off of the xenon. Once even just a tiny bit of gas is ionized, the coil's not insubstantial electric field plus changing magnetic field whips free electrons sideways into neighboring atoms and sets off a whole cascade of ionization near the coil. The trick is getting that initial spark started. The simplest approach is to kinda twist and grind the glass globe against the coil. Rubbing dissimilar materials together causes a buildup of static electricity, which can produce electric fields strong enough for local ionization. For my project, though, I wanted electronic push-button start. And in order to do that, I need to generate a brief but very high voltage pulse, which is capable of ionizing the xenon gas even through the walls of the glass vessel. My approach borrows from the technology of xenon flash lamps. They've fallen out of favor as LEDs have gained supremacy, but this kind of circuit used to be in just about every disposable flash camera. Here's the diagram. I feed in a kinda high voltage source from over here to charge up this little capacitor, but it can't discharge since there's no actual path to ground. The path to ground is through this device, which is an old school kind of circuit protection called a gas discharge tube, or GDT. It's basically a tiny spark gap with some kind of low pressure gas mix designed to break down at a specific design voltage, in this case at 300 volts. Once it does, the charge in the capacitor is released almost instantly. Stored charge in the near plate of the capacitor dumps to ground through the GDT, but the far side also has an equal and opposite charge. That charge flows through this special kind of transformer, called a trigger transformer, which is used pretty much exclusively for xenon flash lamps. This transformer converts the 300 volt pulse to as much as 3 kilovolts on this little wire pressed up against the outside of the glass. You can actually see light from the electrical flashes inside the GDT, and long sparks at the transformer output off of the flywire. This whole trigger module needs 300 plus volts of input power, so let's zoom out a bit. To get that voltage, I'm using this specialty chip LT3420 to drive a miniaturized flyback transformer. So I have a flyback transformer to charge up a capacitor, which discharges a spark through the GDT, creating a pulse feeding another transformer to make a higher voltage spark to activate the plasma toroid, which is basically operating as a big, flashy transformer. Hell yeah. From here, there's just a few more loose ends to tie up. If I allow the toroid to run at maximum power, pretty soon the MOSFETs start to overheat. When the MOSFETs get past about, 100 degrees C, I get a red warning light. It's just a red light, I still need to reduce the power myself, but the warning is nice. This whole time, there's also been a heatsink and fan hiding underneath the board. The fancy brown fan might be inaudible, but it's highly necessary for pulling heat out of the circuit. In order to get the full 20 volts of modern USB-C power delivery, I'm using this little off-the-shelf module down here. Its entire purpose in life is to very politely ask the upstream USB power supply for the full voltage and amperage that we're looking for. Now, at this point, you may be asking, hey, can I get one of these, and could I use it as a desk toy? Well, unfortunately there are a few issues. This device presents a few very real hazards that need to be discussed. There's hazards thermal, electrical, electromagnetic, and radioemissive. First, the thermal hazards. At low power, this device is happy to run indefinitely. The hottest part will become the glass envelope. However, at very high powers, it will gradually overheat, and it'll especially overheat if it's allowed to run without any plasma or ionization to act as load. In some of the earlier prototypes, you can see a few components that are visibly scorched due to this kind of overheating. The device is pretty stable, but not so stable that I'd completely trust it to run unsupervised. Now on to the electrical hazards. If you touch this little area of the board marked HV, you'll get a small but painful high-frequency, high-voltage RF burn. This isn't like a normal electrical shock. The frequency is high enough that your nerves don't register it as that zapping feeling, but instead it's a kind of pinpoint searing sensation that then takes a few days to fully develop into a burn. I carelessly got a few during testing. It's not the end of the world, but not really recommended either. Additionally, parts of the coil are high voltage enough that they will shock you even through the transparent solder mask. I've placed those on the underside of the board to try and reduce that risk, but still, you shouldn't touch them. Early versions of this design had a transparent safety shield over the top of the entire board, but I decided that looked really silly, so I removed it. In this case, again, the safety strategy is don't touch it. My bigger worry is actually the electromagnetic hazards. In the immediate vicinity, in the near field, this device puts out a hefty amount of electromagnetic radiation. This isn't just abstract or theoretical either. I've seen my lights flicker from spurious inputs on their touch buttons. I've seen my little weather station nearby flicker. And at one point when I displayed this to a few friends, one critter actually had their cell phone completely stop registering touch input for a couple of minutes. I would genuinely not want this device operated near any kind of safety critical electronics. That means more than just don't run it in a hospital or run it on an airplane. There's folks in this world who have things like insulin pumps, hearing aids, pacemakers, and you might not know who that is just from looking at someone. Even if it would probably fine really isn't good enough when it comes to risking someone else's health. And finally, the radio hazards. Inherent to the function of this device is the emission of far-field radio waves. This isn't the result of poor design. In order to work, this apparatus needs to be wiggling the electromagnetic field, and some of those wiggles will propagate as radio. It's not a huge issue to run this apparatus for a few minutes at a time for a demo, but I really wouldn't want to be just leaving it on for hours at a stretch. It's kind of poor form to spam the electromagnetic spectrum, and I certainly don't need the wrath of either the FCC or any local amateur radio operators. So after all those warnings, maybe you're still asking, hey, can I build one of these? And my answer is, hell yes you can. You should. My entire build and my entire design is all open source. On my hackaday.io page, I have a full schematic, I have a bill of materials, I have PCB design and fabrication files, I have more. Also, if you want to use one of this specific black FR4 and clear solder mask boards, I have a few extra for sale, and I'll happily sell you one if you drop me a message there. And if you're thinking, hey, I don't want to just copy this exact design, even better. I also have stuff like more notes on circuit theory, recommendations for things like component selection, etc. My favorite part is that this build, the one you're looking at, also does have some real design deficiencies, and I would love to see you make something even better. That's it. Next video is going to come out next time I do something really cool. See ya.